Hey guys, let's go ahead and go over 9.4. So we're going to do a couple of comparison tests on this section. So now first you can copy that down. I don't think it's that clear about how to get the direct comparison test. And here are the two things you need to remember. But mainly, I think the verbal description is better. So if a series is converging, then compare it to a converging series. The series you compare must be larger, all right? Now, if you think a series is diverges, then compare it to a diverging series. The series you compare it to should be smaller, right? So this is how you use the comparison test. First, you need to figure out, and this is something that I wrote ahead of time, but again, it's something you need to come up with. You need to come up with a simpler version of this. A simpler version of that. Okay, so now that you come up with something like this, hopefully, they need to decide whether this right here is convergent or divergent. But before you do that, you need to figure out which one's bigger. Meaning I need to compare those two sequences, or those two sums, if you will. And I need to figure out which one's bigger. All right, now in this case, this one's going to be bigger. Okay? So now, and again, sometimes it's really easy to tell whether something's going to be bigger. Sometimes you might have to plug in a couple of, a few of those numbers from the sequence and just see which one's getting bigger, all right, or smaller. So in this case, that's going to be bigger. Okay, so notice that what this says right here, okay, is that the series that I'm comparing it to is going to be smaller. All right, so this right here is smaller, and that's kind of the important part. Okay, so let me write that in red because the description, I think, gets a little bit confusing, right? So I'm just going to write smaller here. Not that you didn't know that, but the inequality, but now we know which one to use, right? So now we're going to see whether this right here is convergent or divergent, all right? So hopefully you notice, and you're going to have to use the skills you've acquired in the past 3 lessons, okay, that this right here is a p-series. So what that means to you is that we're going to say on here, since p is equal to 1/3, and 1/3 is between 0 and 1, then this right here diverges. Okay, so what does that mean to you? According to what we have, that actually fits the second one. It fits this one. All right, so it's funny that they said if you think the series diverges. So really, at that point, you don't really do that. You figure out which one's smaller or bigger, and then you do this. All right, so according to this, because of the direct comparison test, so by the direct comparison test, that's a letter D, by the way. Then this right here also diverges. All right, let's take a look at B, all right? So again, sometimes the hard part is to figure out a simpler series to compare it to. So we're going to compare it to that series right there. Now, remember, what I have to do first is I need to figure out which one's bigger. Is between these two right here, which sum is going to be bigger? And again, if you didn't know that, just at least in your head, start plugging in a 1 and a 2 and a 3 for n and see what happens, right? Now, if you do it enough times, you realize that that's going to be bigger. Okay? Now, that is going to fit into the first one, all right? It's going to fit into this one right here. So now that I know it's bigger, if it's converging, if this series that I have right here, if it's converging, then that's going to make this series, that series right there also converging. All right. And if it's the opposite, then it's inconclusive. We don't know. Okay. So let's go ahead and write this. So again, hopefully you notice that this is a geometric sequence. Let me see how I'm writing geometric sequences here. And again, what the number is really not important, but this right here is convergent. Let me see how they wrote it in the homework. They just wrote convergent geometric series, which it is, so hopefully you recognize that it is. The geometric series is one of the two that I can think of where we can actually find a sum using a formula, but we're not asked for that. Okay, all we care about is basically because this right here, the ratio 2/3 is is less than 1, and that's going to be convergent. Okay, so because that's what is convergent, then by the direct comparison test, this sum will also be converging. All right. So let's go to C. All right. So same thing. We're going to try to figure out an easier way to figure out what to compare this to. Right now, on this one in particular, we can compare it. Now, first of all, notice that I could compare it to this, but if I simplify that, that would actually simplify to this, right? Okay. So that's gonna be comparing to that. Now, I have to figure out which one is bigger. Okay, and to do that, you may have to do a few, right? If I call this, let's see, for the first one, if I plug in a 1 here, I would get and I'm just writing some numbers that would help me. All right, so if I look, even if you want to use a calculator, it's fine. But basically, these are the first numbers of this one. Okay, and the first numbers, let me write a few more here, just one more. You have to look at least a few, all right? At least a few numbers here. Now, for the other one, we would have 1. This is for this one right here. We would have 1, 1/4, 1/9, 1/16. Okay, so hopefully you'll notice that this one right here is going to be bigger, right? Which means that that's going to be bigger. Okay, so let me erase that. That's just sort of the thinking you want to do sometimes. Okay. So remember, this is bigger. Now, on the bigger, since what I'm comparing to is bigger, then this better be converging. And if it doesn't, then that's inconclusive. Okay, so 1 over n squared, this is also a P series, okay? So this is convergent. Let's see, is what I'm telling you true? Yes. Convergent P series. I guess for your sake, I would at least write y. I would say P is equal to 2. And P is greater than 1, so therefore it converges, okay, according to what I wrote earlier for you. Okay, so because that's converging, by the direct comparison test, this more complicated sum also will converge. Okay. All right, let's do example D. Now, to come up with a better, kind of the same idea as the last one, I'm going to compare it to n squared over n cubed, but that's going to give me 1 over n, which is our harmonic sum. And the power will be 1 here, which is important because I know this is going to be divergent, okay? So what I'm hoping for is that this right here is greater than 1 over n. And again, if you do the same method as I did last time where you're just plugging in n is equal to 1, n is equal to 2, 3, 4, 5, eventually you'll find out that this one is indeed bigger, all right, which is good. So it's going to fit into the second one. So what we're hoping for, I think my wife is watching American Idol in the next room. What we're hoping for is that this right here is divergent, because I would conclude that by the direct comparison test that it will be divergent. If it's not, if it was convergent, then it's inconclusive. I wouldn't know either way. I wouldn't know whether it's convergent or divergent. So this is convergent by, divergent. Whoops. Divergent P series. P is equal to 1. Okay. Now, because I know that by the direct comparison test, this right here also diverges. Okay, now it says, can the direct comparison fail? Now, I wouldn't say failed, but basically, all right, if you look at these, and again, you can do the comparison here, and I'm going to write some numbers real quick. If I were to add this sum, and so on, of course. And this one right here, you have a 1/2 plus a 1/4 plus a 1/8. 1 over 16 plus 1 over 32nd. Okay, so that means that this right here, a of n, is bigger than b of n. So again, this in this case is smaller. All right, so what I'm hoping for, if this would work, is that it diverges, okay? So what would happen on this one right here, let's say that we know how to find where this is convergent or divergent. All right, so what would happen after that is that we're not sure. Let's say that this right here, let's say that this was divergent. Or convergent, excuse me. Then, well, the series converge, we're not sure, okay, because that's not how this works. It has to fit into these two scenarios right here. Has to fit into those two, which is the examples that I give you here. And if it doesn't, then you can't really conclude anything, okay? So let's go to another comparison test called the limit comparison test. Okay, and I think, is that it? 2 problems? Yeah. All right. So on a direct comparison test, all right, this is what we would do. Now, first of all, like if I were to try to compare this to something simpler like this, okay, that would mean, like if I were trying to do the, what does that call? The direct comparison test, right? So give me a second just to write this, and do not write this because I'm going to erase it. If I were trying to figure out which one's bigger, let's see, we know it's less than a of n. So is that bigger? Is that true? Okay. So if that one's smaller, we would be basically hoping that this is divergent, but it's not. This is convergent. All right, so a direct comparison test cannot help us here because it's not going to tell us whether it is or it's not. Okay, we don't know. It's inconclusive. So therefore, we have to find another way to do this. And now this is where the limit comparison test works. It also works if you have something kind of messy that will be hard to find. Okay, so now this is what we're going to do. All right, we're going to basically take the limit. We're going to take the limit as n goes to infinity. Notice that I'm just using their definition, which is right here. Now, a of n is your original function. And then we're going to divide that by a comparable function, which is this, right? Now, if I keep change and flip, that would give me 2n cubed over n cubed plus 4. Now remember that I could divide each term by n cubed, and that would give me 2, or in this case, I can use the horizontal asymptote test. Or not the test, but method, I should say. But long story short, the limit is 2, okay? So this is let me read this now. Okay, so because that number that I just found is between 0 and infinity, duh. Okay. Then by the comparison test, the limit comparison test. Oh, wait a minute. Let me think about it for a second. I also have to make sure that this right here is also convergent or divergent, right? Now you should know that right there is also convergent. And I'll write it in blue here just to kind of distinguish it. It's a convergent P series where P is greater than 1. Okay? So because this is true, and because this is convergent, and this is also convergent, or excuse me, because this is between 0 and infinity, then by the limit comparison test, both series will converge. So again, that was kind of messy what I just said, all right? So just to make sure, and let me look at the homework so I can kind of see what we did on some of the limit comparison tests. You have to make sure that whatever you're comparing to is either convergent or divergent. It doesn't matter which one at the point. And then now, if what you get here is a number, all right, then that's basically going to make this converge or diverge. So let me show you another example, because that's the part that's a little bit confusing. I want to make sure we understand. All right, so let's go to the next one. So now, this one a little bit more confusing. We're going to compare this to something simpler than this, like 1 over, let's see, 1 over n. Now, I know that 1 over n is divergent. Okay, so I want you to, and this is the part that's funny. That doesn't mean anything, all right? So it's only going to help you for the next step. So now I still have to use the limit. I have to do what I did last time, where I have the limit as n goes to infinity of this right here, which is what they call a on that formula. And then divided by 1 over n, which is the same thing as multiplying it by n. I just do a little bit of the math here. This right here is going to give me n to the fifth plus 5 n over 4n to the fifth minus 2n to the third plus 3. Now, this right here, the limit is going to be 1 over 4. Now, that number, 1/4, is between 0 and positive infinity. All right, so by, and this is a confusing part for a lot of people, by the limit comparison test, because I got something that's between 0 and infinity, and this is divergent, then both series will diverge. Okay, so let me reiterate that one more time, okay? You first need to find a way to find a hopefully easier equation to compare it to. Once you have found that, then you need to figure out if it's convergent or divergent, okay? Once you decide that, then you still have to take this, you have to do the formula for the limit comparison test, which is right here. And if that gives you a number that's between 0 and infinity, if the thing you're comparing to was convergent, then this will also, oops, let me write it with this. And this will also, this will also be convergent. All right. And this one right here, since this one's divergent and this happened to have an answer, then this will also be divergent. Okay. So it's a little bit weird. Again, please ask me questions if you got them. All right. This is basically the end of the comparing the basically just the very basic sequences and series. And we're going to move on to something more difficult after this. Okay. We'll see if we'll have a test or not. We'll just see.